Welcome back to Physics 142. We've been talking about circuits and analyzing circuits that have resistors in them and analyzing circuits that have capacitors in them. But one thing that we haven't talked about yet is what if we have a circuit that has both a resistor and a capacitor in it? How do we handle circuits, or what is the behavior of circuits that have resistors and capacitors, which we often refer to as RC circuits since they have resistors and capacitors. So I've drawn just a typical RC circuit here as an example, all right? And what I have is I have a power supply that's going to give us some potential V, and then here's a resistor, here's a capacitor, and I've added a switch, all right? Because what we're going to want to think is what happens isn't necessarily going to be constant with time. When we close the switch, things might change with time, and so we want to put a switch in to think about those changes with time. And specifically, capacitors, usually they start with no charge on them, right? They're going to start with no charge. And when we just had a capacitor, if we closed the switch, then the capacitor would charge up really quickly, right? It would basically almost instantaneously go to have some charge Q on that capacitor. But the resistor is going to resist the flow of current. So if we want to think about what happens when we close this switch, the capacitor is still going to want to charge up. Q is still going to want to flow off the power supply onto the capacitor, right? We're still going to want to get some charge from that power supply onto the capacitor and have it charge up over time. But the resistor is going to slow that process down, right? It's going to keep some of that current from flowing onto the capacitor. At least it's going to, make it take some time. So what will happen when we close this switch sort of conceptually is the capacitor will still charge, it will still acquire Q, but it won't be instantaneous. It will take some time, all right? And so one of the things we want to figure out then is sort of how long does it take, right? And once that capacitor is fully charged, then what happens, right? And we could guess that once it's fully charged, once you have all the Q there, well then no more Q wants to flow and you're not going to get any current at all, right? Okay, so how do we talk about this mathematically? Well, actually RC circuits you can also analyze using Kirchhoff's laws, his junction rule and his loop rule. And specifically, I wanted to think about the loop rule, or sometimes it's referred to as the voltage rule for this circuit, all right? And so to do that, what we want to think about is that all the potential changes around the circuit, when we go in one full loop, all the potential changes around that circuit should still add up to 0, okay? So let's go ahead and draw in a loop here and see what happens, all right? So let's start here, all right? And then we'll go across the power supply. So we're going to gain some potential going across the power supply. So we'll gain a potential V, all right? And then we'll go around and we're going to go across the resistor. And now we need to know what direction the current is flowing in the resistor. And current usually flows from positive to negative, right? So our current going to be flowing this direction. So if we're going with the current, right, from plus to minus, that means we're going downhill. So we're going to lose potential going across the resistor. So specifically, we'll lose I times R's worth of potential. All right, and then we get to the capacitor. Well, how do we deal with going across the capacitor? Well, capacitors, remember, they have plus Q. This is the plus side. This is the minus side here, right? And capacitors have a potential across them, a potential V, right? And you might recall, just note down here that C, our capacitance, was Q over V. So that means V must be Q over C, right? And so specifically here, as we go from the positive to negative, we're going to go more downhill, right? We'll lose more potential. And how much will we lose? Well, we'll lose Q over C. So for the capacitor, we'll have minus Q over C is the potential drop going across that capacitor, right? And then we're going to get back to where we started. So that whole thing must equal 0. Now, the trick here is, well, what do we do next, right? If we want to know sort of how much current is flowing at certain times, right? We want to know how much current there is, and we want to know how much charge is on the capacitor as a function of time. And here we actually have a problem because current, you recall, is related to Q. And specifically, current is the derivative of Q, right? It's dQ dt. And so if we write that in here, we have V minus dQ dt times R minus Q over C equals 0. And this is a differential equation, right? It's something we had similar things at the beginning of the semester, right? Where we have a derivative and an amount in the same equation, right? Where the rate of change in the charge depends on how much charge you have. So, we could rearrange this, right? Maybe I could solve for dq dt or something like that. That rate of change would be 1 over r times v minus q over c. But to actually figure out how this equation works, we would need to use our sort of differential equations math. Right? And that's not a prerequisite for this course. So keep taking math. You'll figure out how to solve this, but we can sort of guess what the equation must be like, all right? And specifically, if we need something where when we take the derivative, it's equal, right? With maybe some other term here, right? But clearly we need a function where when we take its derivative, we get the same thing back, and that's going to be some sort of exponential function, right? Exponentials are the things that when we take one derivative, we can write down equalities, right? That when you take a derivative of an exponential, it gives you back what you started. So if you go ahead and solve this differential equation, you end up getting the following answer, all right? And so I'll write it down. It ends up having an exponential in it, but there's these two terms, so clearly there's going to be something going on with the two terms, right? So the answer to this differential equation, the solution to this differential equation, the equation that works, all right, for it, is that you get Q as a function of T on the capacitor. So the amount of Q on that capacitor as a function of time, all right, ends up being C times V times 1 minus e to the minus t over RC. All right, so this, an important equation right here, all right, this is the amount of charge on a capacitor as a function of time, all right? So this is amount of charge on the capacitor as a function of time. And I'd like to notice that hopefully this makes some sense, all right? So t is time. So if we plug in time equals 0, then we'd have e to the 0, and we'd have 1 minus e to the 0. E to the 0 is 1, so 1 minus 1 is 0. So at time equals 0, we'd have no charge on the capacitor, right? So maybe we could even draw a graph of this. So let's go ahead and draw a graph, all right? So we're in a graph. It's a function of time, the amount of Q that's on the capacitor. And what we realize, if we put in time equals 0, there's no charge on the capacitor, right? So 0 at time equals 0, we have 0 charge, all right? And hopefully that makes some sense. But now if we think about a long time later, right? So if we make t really big, all right, then if we take t to be really, really big, infinitely long time later, then we would have e to the minus infinity, or e to the minus a large number, which is very close to 0. And we get 1 minus 0 here, so we'd just be left with CV minus 0, right? So after a long time, all right, after a long time, we're going to reach some value, and that value that we reach, all right, is specifically the value C times V, which is actually makes sense, right? That Q for a fully charged capacitor is C times V. We already had that equation for capacitors, so it makes sense that after a long time, we reach C times V, okay? But in between, we sort of have this exponential charging of it, all right? Where at the beginning, and we end up charging it really quickly. All right, and by the end, we're just charging it little bit by little bit by little bit. And so the curve ends up looking something like this. All right. One thing that I should note is that this RC sometimes gets written with the letter tau. All right, so tau is RC. And this gets a special name. It's called the capacitive time constant, right? Capacitive time constant. And it's just a convenient value where we can sort of compare how quickly things get charged. Because basically, when you've charged it up to RC, then that's e to the minus 1, right? And that means you've charged it up to about 63% of its value. All right, so that ends up being maybe about in here or so, all right, is maybe this is time equals tau equals r times c, all right, and that is helps you compare sort of how charged up things are. So every rc that of time that passes, you get another e to the minus 1 sort of closer to being fully charged. All right, so this is just a way that we can represent how quickly things are being charged. It is interesting to work out. You should look at the units. If you take resistance times capacitance, you do actually get time. It's kind of cool thing. I'll leave that as an exercise. All right. Okay, well, one other thing that we should think about here is this is the amount of charge on the capacitor. What about the amount of current that's flowing over time? Like the current going through the resistor as a function of time. Well, current, we said, is the derivative of charge, right? So that means that we should be able to take the derivative and see what happens, all right? So let's do that. So what about current? So let's do that over here, current. All right, what about current? Well, current, we need to take the derivative, dq dt, all right? So that's going to be ddt of this thing, of CV minus CVe to the minus tau over RC, right? And we're taking the derivative with respect to time, all right? And so this term ends up just being a constant, all right? And here, when we take the derivative, we end up getting an RC that comes down, right? A 1 over a minus 1 over RC that comes down. And so what we end up getting is that we get that I of t, right? This dq dt ends up being V over R, because we had 1 over RC, so the C's cancel. We're just left with V over R. The minus signs cancel, so it becomes positive. And then e to the minus t over RC, right? That's the derivative of that function there. And so if we make a graph of what this current looks like as a function of time, right? So let's look at time current as a function of time. All right, at the very beginning, all right, when we plug in time equals 0, when we plug in time equals 0, we get e to the 0, which is 1. So that means at the very beginning, the current, right, the current here at the very beginning is just V over R. All right, that's the amount of current we have at the beginning, and that hopefully makes some sense to you, right? Current is V over R. That would be just like a normal circuit, right? But then very quickly, this is an exponential drop off, right? So over time, that current is going to drop off exponentially. Whoops, actually hit 0, right? But gets close, okay? Drops off. And again, the sort of way that we can quantify how quickly is it drop off by 63% in RC's worth of time, right? So we would note that, right here, this would be T equals tau equals RC. So to sort of summarize this then, what can we take from this? All right, well, let's think about the behavior right after the switch closes, right? Right after the switch closes, we have full current, right? And basically no charge on the capacitor. So essentially, right after you close the switch, you can treat capacitors like wires. So let's note that, all right? Right after, right, immediately after you close the switch, then the capacitor acts like a wire, right, because all the current's flowing. All the current is flowing here, all right? The capacitor is acting like a wire. However, if instead we think about a long time later, all right, a long time later, well, after a long time, the current is essentially dropped off to zero, right, because it's fully charged up. So after a long time, you've no more current flowing. Well, essentially that capacitor is then acting like an infinite resistor, right? The capacitor acts like an infinite resistor. All right, it doesn't allow any current to flow after a long time once it gets fully charged up. And so we can do an example of this, all right, and I will do that in the next video.